Section 2.2 is the inverse of a matrix. This is a rather important section. We've already defined the product of two matrices, so long as their sizes match in an appropriate way, that it's well defined. So we've got multiplication of two matrices. The question is whether or not we have multiplicative inverses. So if you remember, in this space of real numbers, we have the number 3. It has multiplicative inverse 1/3, right? So 3 times 1/3, and that's equal to the multiplicative identity of 1, right? Any number times 1 is equal to that number. So the question here is, well, the question that's settled in real numbers is that, yes, if we're given any non-zero real number, then we can multiply it by another number that's equal to 1, and namely that other number is 1 over the given number. So in this case, we had 3, and then 1 over 3 brought us back to 1. Very straightforward, well-known property of real numbers. The question is whether or not we can take two matrices, or matrix A, and find A inverse. That's how we'll read this, A to the -1, such that A times A inverse is equal to the identity matrix in that space, right? So what we'd have to note right away is that A must be a square matrix, right? N by N, so that its inverse is also N by N, so that when we multiply them together, we get an N by N matrix. So we have to be square. Our rows and columns have to be equal to each other in order for this to be well defined. Because remember that matrix multiplication is not commutative, so we have to write A inverse times A as well. Both of these conditions need to be met. It's not guaranteed for two matrices that one times the other is equal to the reverse of that order. So in the definition of our matrix inverses, we have to write both of these statements down. And that's exactly what we see below in the notes. We have A times C. We're not calling it A inverse immediately, right? C times A and A times C is equal to the identity matrix in that space, or I sub n, because we're dealing with N by N matrices. So A is invertible if there exists an N by N C matrix that satisfies both of these equations. So furthermore, the inverse matrix is unique. This can be demonstrated by the associative property of matrices. If we were to write that down and say, okay, suppose there are two matrices. Suppose B and C are inverses of A. Now I might not show all of the, or both directions here, but if we had B and C were inverses of A, then we know that A times C is equal to the identity matrix, which is equal to A times B, which is also the identity matrix. If these two things are equal to each other, then we could multiply both sides by C perhaps, right? We could write something like this: CAC is equal to CAB, applying both sides on the left, and we'd have that, well, this is just I as well as this, and I times C is just C, and I times B is B. We see that, well, the identity matrices don't really need to be there. It's like multiplication by 1, and that's telling us that C is equal to B. Thus, if we were to declare, we see that if we declare there are two inverses of A, then those two inverses must be equal to each other. So it really means there's only one inverse of A. It's a common method for demonstrating uniqueness. And that wasn't a complete proof of it, but it was just a sketch of how such a thing might come about. So since this matrix is unique, we'll sort of adopt our notation from real numbers and use this -1 exponent to discuss, or to denote, the inverse matrix of a matrix A. And now we have this inverse statement that we were seeking at the very beginning of this discussion. So it's possible that a matrix does not have an inverse, A inverse, right? We'll see matrices that don't have such a matrix inverse, and we'll call those singular matrices, or we'll call that matrix a singular matrix. And any matrix that is invertible we'll call a non-singular matrix. We'll, in later sections, dig a little deeper into implications for singular and non-singular matrices. But for now, we're really focused on finding inverses. The first thing we should do is just meet a couple inverses, right? Let's verify that two matrices are inverses of each other, or that a matrix A given in this problem has the inverse B given here. So the way to confirm that this is the case is to multiply A times B and see that we get the identity matrix in R3. So in other words, that we get a 3 by 3 identity matrix. When we do that, first row, first column here, we'll get this 1, and the reader can check that the details of this multiplication actually do work out. Remember, this is 0 times 5 minus, we'll say 0 times 5 minus 1 times -1 plus 1 times 0, right? Or 0 times 5 plus -1 times -1 plus 1 times 0. And we see that the only term that's not 0 are the middle multiples, -1 times -1, that's +1. And that's what we end up with in this entry. But of course, that's just matrix multiplication. Now, I'll leave as an exercise the details of B times A equals the identity matrix. Remember, we do have to check both ways because matrix multiplication is not commutative. Now, that's all well and good. And we see, okay, we can confirm whether or not a matrix has an inverse, but what we'd really like to be able to do is calculate the inverse, right? We want to know how to find such a matrix B as in this example. So one of the simplest cases is the 2 by 2, and that's where we have a matrix A with entries A, B, C, D, reading along the rows. And the theorem here tells us that if A times D minus B times C is non-zero, then A is invertible, and A inverse is given by this formula here. So we can check whether or not the matrix has an inverse through this number here. This is called the determinant of A. We're naming it down here, denoted as DET for determinant of A, and it's just AD minus BC. Notice that this is really a diagonal, A times D minus B times C, cutting the other way. So if this number is non-zero, then A is invertible, and it has this formula. We see that this formula looks more or less like the entries of A itself. Now, what happens is we flip along the diagonal, so A and D swap positions and keep their signs, and we just change the signs of B and C. It's kind of a pretty easy formula to commit to memory. Swap along the main diagonal and negate the off diagonal. So how does this formula come about? Why does it work? I won't go through all the details of the proof. That is an exercise in the textbook, but one thing I can show you is this. If we took the matrix A and put it into row echelon form, well, the first thing we do is divide the first row by A, right? And we'd have, maybe I write this as arrows. Standard way we've been denoting it. A and then B over A. I want to put a leading 1 right here. We have C and D. I've now got a leading 1 in my my first row, first column. So I'll get rid of the C down below. So that's C times the first row, and then we're subtracting that from the second row. So the first row is unchanged, and we have 0, and then we have BC. Oops, we have D minus B times C over A. So that came about. And if we wanted to put a leading 1 here, or multiply both sides by A to make this maybe a little bit more, put this in, connect this to the determinant, which is the goal of this. We have 1 B over A, and then multiply the second row by A, just so we have something that looks like this, AD minus BC. Okay, so once we look at this and realize this is the row echelon form of A, it's not the reduced echelon form, but we don't need to go that far because we can make some inferences about this. If this were to be a 0, then we've got a row of zeros in A's echelon form, which means that it doesn't have a pivot position in this row, which means that it doesn't have a unique solution to the vector or the matrix equation AX equals 0. right, to the homogeneous problem. We'll have multiple solutions, right? Because we'll have a free variable if this is equal to 0. Namely, x2 would be free, right? And again, this is considering the augmented matrix, putting 0, 0 here is our third column for our right-hand side. The first two columns are the coefficients of the system. And yeah, if this is a 0, then we have a free variable, which means we have infinitely many solutions, which means that this has non-unique solutions. And if that's the case, what kind of trouble could that be for an inverse matrix? Well, that means we could have an x and a y that are not equal to each other. So suppose we have two variables two vectors x and y, which are not equal to each other, but ax equals the 0 vector and ay is equal to the 0 vector. Well, if we apply A inverse to both sides of this, we get an equivalent equation, which is A inverse times ax, and A inverse times ay just leaves us with x and y, and we'll get a contradiction. This thing tells us that x must be equal to y if inverse matrices A exist. So we see that we could run into a contradiction. Now, there's an exercise in the book, numbers 35 and 36, that'll walk you through these proofs. And they make it a little bit more explicit. They have the student construct two vectors, x and y, that are actually not equal to each other, yet they're both solutions of the homogeneous system. So you can go a little further to see even more detail there. But the idea is that if a matrix doesn't have a full set of pivot positions in it, an n by n matrix doesn't have a full set of pivot positions, then we have non-unique solutions to the homogeneous equation. And when you have non-unique solutions to the homogeneous equation, you'll always be led into this sort of contradiction. So you cannot have an inverse for such a matrix. And that's an important bit of intuition that hopefully as you work on these problems becomes a bit more apparent and easier to understand. But nonetheless, we're really on a mission to figure out how to invert a given n by n matrix. So let's continue in that regard. First, we can practice the formula given on the previous page. They ask us to find the inverse of this 2 by 2 matrix. We'll remember that A inverse is given by this general formula, 1 over AD minus BC, or we could just write 1 over the determinant of A, since we've already defined that. And this is, we swap these positions, right? D and A swap, and we have negative C and negative B. B and C stay in their positions. We just change their plus or minus signs. So for the determinant, A times D, that's 1 times 2 minus 3 times 4. And this is all times matrix 2 and 1 swapped on the main diagonal, and then negative 3, negative 4. And continuing the work to simplify, we have 1 over 2 minus 12 is negative 10 times this matrix. This is a reasonable way to write it, but really we should probably take it all the way into just a 2 by 2 matrix and not a scalar multiple times the matrix. And we'll have negative 1/5 for 2 over negative 10, 3/10. Moving along the rows, 4/10 is 2/5, and negative 1/10. So we can check when we're done with this, and it's a little bit of work to do both really to calculate it, but we could also check when we're done that this is the inverse of A. In other words, we can multiply this given matrix here by this matrix and confirm that we do in fact have an inverse. So it's easy to check your work when you calculate an inverse matrix. You just confirm that the product of the two matrices is the identity. You could check both sides too if you really want to be very thorough. So this matrix times A on the left, and then this matrix times A on the right. But typically one direction is just fine. Okay, so we're going to build up a few theorems in this section, some of which are more useful than others. But really, in terms of understanding properties of inverses, it's probably worthwhile to pay a little bit of attention to each of the theorems in this section. And I'll sketch proofs wherever I can in these notes, or at least discuss the intuition for most of these results as well. So if A is an n by n invertible matrix, then for each B and Rn, each vector in Rn, the equation Ax equals B has the unique solution A inverse times B. So this is really talking about our first use of an inverse or an inverse matrix. So why would we want to find an inverse? Well, if we know that a matrix A has an inverse, then we can go back to this system we've been dealing with since the beginning of the course. We can solve it by multiplying both sides of this equation by A inverse on the left. And what we end up with is X on the left-hand side, because A inverse times A cancels, and we have A inverse times B on the right. So if we let A and B be as defined in the theorem, so as assumed, an n by n matrix such that Ax equals B has a solution, then we note that X equals A inverse B. We declare that the solution, right? Satisfies this, right? Because A times this substitution of X, here we substitute X as A inverse B, we see that A times A inverse is an A inverse times B is all equal to B because of this cancellation right here. Very obvious. If U and V each satisfy this equation, so now we need to prove uniqueness. So we state that there are two vectors that satisfy this system. Then we see that A times U is B and A times V is B. We just saw something like this in the previous page. Thus AU equals AV. That's just using transitivity of equality here. By multiplying both sides of this latter equation by A inverse, we get U is equal to V. Right, so once again, we've essentially done the same proof I did on the previous page in more of a sketched form. But we see that if we declare two solutions to this system and there's an inverse A, well then these two solutions cannot be distinct. They must be equal to each other. So on the previous page, I argued more with a contradiction statement, but in this page we see that if the solution exists and A is invertible, then the solutions must be unique. So they must be equal to the same single solution. So that pretty much proves that theorem thoroughly and quickly. So use the inverse of the matrix A of the previous example to calculate the solution to the given system. So let's make use. So let's apply a matrix inverse. Is essentially what's happening here. So note that the coefficient matrix A of this system is 1, 3, 4, 2, and that's quite convenient because we happen to have 1, 3, 4, 2's inverse on this page, and that was given by this matrix. So let's take a copy of this. And place it on this page. So we have A inverse is equal to this. And let's solve the system, right? We should have that the vector X, the solution to this, right? If this is an AX equals 5, 10 equation, right? Then X should be equal to A inverse times B. So remember this X is going to be A inverse times this matrix 5, 10. So we can fill in the details of that to get -1/5, 3/10, 2/5, -1/10, 5 and 10 here. And this leaves us with -1/5 times 5 is -1. So first row times the column vector, and then 3/10 times 10 is 3. So we're adding 3 to that. Then we've got 2/5 times 5 is 2, minus 1/10 times 10 is -1. So we have 2, 1 is our solution vector, it appears. Now, the nice thing about this is we could also check this answer, right? Does this vector X solve the equation? Well, one nice way to do that is to multiply it on the left by this matrix 1, 3, 4, 2. We get 2 and 3 is 5, and then for the second row times that vector or that column vector, we'd have 8 and 2 is 10, and it looks like it checks out. I'll let the reader write the details of that one down. So we've now used the matrix inverse to solve a system. It's not the most practical way to go about solving systems, but matrix inverses have a much more useful properties than just solving their systems. So, are there related systems of equations? So another theorem that comes up, and I'll just give the intuition for each of these lines, but if we have an invertible matrix A, then A inverse is also invertible, and its inverse is A. Okay, we'll see some details of that momentarily. If A and B are n by n matrices, then so is AB. That is of course true. The inner dimensions fall out, and the outer dimensions are still n. So we have n by n. And the inverse of AB is the product of the inverses of A and B in reverse order. So it's telling us that AB inverse is equal to B inverse times A inverse. So we'll have a look at why that might be momentarily. And then part C in this theorem is that if A is an invertible matrix, then so is A transpose. And the inverse of A transpose is given by the transpose of A inverse. Okay, that sounds like a mess, but look at it in symbols. So if we're looking for an inverse to A transpose, all we have to do is transpose the matrix A inverse. Okay, so why might these things be? Well, for the first one, we just note that A times A inverse is I, and A inverse times A is I, the identity matrix. Well, that's true because A inverse is A's inverse, right? But we see that A plays the role of A inverse is inverse. So that seems redundant, but it's an easy thing. It essentially falls out of the definition of an invertible matrix A with A inverse as its inverse. So though it is trivial, it does need to be proven, or at least noted that it's the case by theorem. So let's see, in the case of AB, the matrix AB, if A and B are both invertible, well, then B inverse A inverse exists, right? So if we make the product B inverse times A inverse, we see that AB times B inverse A inverse, well, the inside product, B times B inverse, is just I, and that's the identity matrix, so that's just A times A inverse for the two outer matrices, and we end up with this. We know that A times A inverse is I. So we see that at least on one side, the right-hand side multiplication here against AB, that this inverse is actually holding true. If we were to do it on the other side, B inverse A inverse multiplied on the left side, we could see that the A inverse and A matrix cancel, and then the B inverse B matrix cancel, and we'd have both sides of our inverse statement. And that would handle that result. Now for the third part of the result, A times A inverse. Well, remember that this is equal to the identity matrix. So if we take the transpose of this, then we have that this is equal to the identity matrix transposed, which is just equal to the identity matrix. I challenge the reader to check that on their own, that if you transpose the identity matrix, you get the same identity matrix. Well, what does the transpose do? Remember back in section 2.1, we learned that transposes of matrix products switches the order, reverses the order, right? So we have A inverse transpose times A transpose, and that looks like this. But we see now that at least one side of this, and we can write it the other way by swapping the order inside here. So we get both sides to prove this inverse statement for the transpose matrix. But we see that A inverse transpose times A transpose is the identity matrix. So we see that A transpose's inverse matrix, so A transpose's inverse matrix is the matrix given here. If we do it the other way, we confirm that absolutely. So that's just a quick sketch of the proof of that result as well. These are all nice properties to have floating around when we're dealing with matrix inverses. So how does a matrix inverse come about in a larger matrix? So this takes a little bit more work than the 2x2 case, but the good news is once we've done it for the n-dimensional case, then we're all set for any sized matrix. We'll mostly look at 3x3s because they're the smallest version of the general case. We'll prove things in terms of n by n matrices, but we'll our examples will deal with 3x3s because they're computationally less intense. So an elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. And we'll typically talk about elementary matrices in this section as matrices capital E with some kind of subscript, because we'll typically have a series of these matrices multiplied together against a matrix A. For now, we're just going to consider what happens with a single matrix, elementary matrix times A. Now, an elementary matrix, let's see, is a matrix obtained by taking the identity matrix with ones on the diagonal and zeros elsewhere, and then performing a single row operation. So in the case of E1, we've taken 2 times row 1 and added it to row 3. One single row operation converted the identity matrix to E1. Similarly, E2, we swapped rows 1 and 2 in the identity matrix to get E2. And then for E1, we multiplied the first row by 3, again, a single row operation on the identity matrix to end up with this. So that's our definition for elementary matrices. And it turns out these are very fundamental pieces of the matrix inverse problem. So let's take a general matrix A with these entries, A through the letter I, leading along the rows. And we're asked to compute the product of each of these. So what's the effect of this E1 matrix, which again was formed by taking 2 times row 1 and adding it to row 3? Well, if we carry out this product down here, E1 times the matrix A, we see that the first 2 rows, we just end up with the same rows that the matching rows for A, but the second or the third row of A is equal to 2 times the first row plus the third row. So the same row operation that formed our matrix, our elementary matrix E1, is this. When we multiply this elementary matrix times A, we have that same row operation performed here, which is a really nice sort of mirroring property, right? However, we form the elementary matrix, that's the thing that it does, or the row operation that it does to any other matrix when they're multiplied times each other. So we check for E2. E2 will swap rows 1 and 2. So if you carry out this multiplication, write down what E2 is multiplied by A, you'll see in the details that this is the case. So again, an elementary matrix, the row operation that formed the elementary matrix is the same operation that the matrix does to any other matrix it's multiplied by on the left. Keep that straight. We're multiplying our elementary matrices on the left of our given matrix. And for E3, it's 3 times the first row, and we see if we carry out E3 as a matrix multiple against A, that we'll get 3 times the first row of A, and everything else remains unchanged. So those are our elementary matrices, and they've got some very nice properties. Down below, we see that if an elementary row operation is performed on an m by m matrix A, the resulting matrix can be written as EA, which is summarizing exactly what we've seen in this example. Whatever row operation formed the elementary matrix, it's exactly what E times A does to A. So, and A doesn't necessarily have to be n by n. Notice that it's an m by n, and this does in fact work, but we will mostly apply them to n by n matrices because we're going to talk about square matrices A in regards to their inverses. But it is nice that these things do also work on more general rectangular matrices. So moreover, we can assert that each elementary matrix E is invertible. So the inverse of E is the elementary matrix of the same type that transforms E back into I. Okay, so it's pretty easy to see how that might be the case, right? So all you have to do is recognize what type of matrix, or what type of row operation an elementary matrix does. And in this case, 1, 0, 0 for E1. Right, this is multiply row 1 by 2 and add that result to row 3. We've already seen that this is what this matrix is. Well, how would we undo that? Well, we would multiply, let's just try to think it through arithmetically. we would leave rows 1 and 2 alone because we haven't changed them with the elementary matrix. But if we subtract 2 times row 1 from row 3, that should undo what E1 did. And just to check that this is the case, what we should write is E1 inverse times E1. And we should check both sides, of course, but this matrix product written down below should yield the identity matrix. And I think if we write it down and carry out this product, we'll see that we do have that result. I'll leave most of these, most of the products, most of the entries in the resulting matrix to the reader to confirm the details of. But if we just check the third row of this result matrix down here, then we're taking the third row of this matrix times the first column. We get -2 plus 0 plus 2. That sums to 0. Third row, middle column, we have -2 times 0 plus 0 times 1 plus 1 times 0. It's all zeros added up. We get another 0. Third column, or third row, third column, we have -2 times 0 plus 0 times 0 plus 1 times 1. We get 1. And it looks like we fixed our third row again. And if you check the details, you should see that the rest of these are in fact this. And you do get the identity matrix for the 3 by 3 matrices. So E2 is a little bit easier. E2's inverse is just itself, right? If we swap rows 1 and 2, then if we swap rows 1 and 2 again, then we're going to be right back where we were. So 0, 1, 0, 1, 0, 0. What I would encourage the reader to do is take this inverse and just convince yourself through the multiplication that you get the identity matrix in 3 by 3 matrices back. And you should indeed have that be the case. Okay, so a permutation elementary matrix is just itself as the inverse, which is very easy. A multiplicative, say, you know, on the previous set of elementary matrices, we had 3 times row 1. Well, 1/3 times row 1 would correct that back, and we'd get our identity matrix back in that case as well. So through these examples, we've essentially seen that we can invert any elementary matrix. We haven't extended that formally, but I think it's sufficient to see that, yeah, for any of our 3 types of row operations with their elementary matrices, it's pretty straightforward to construct an inverse matrix for that elementary matrix. And that's a key part of our matrix inverse theory to come. So the next result tells us that an n by n matrix is invertible if and only if A is row equivalent to I sub n, the identity matrix in that space. And in this case, any sequence of elementary row operations that reduces A to I sub n will also transform I sub n into A inverse. Okay, so sort of 2 results. We have an equivalence statement that A is invertible if and only if it's row equivalent to the identity matrix. And furthermore, what they're saying is that any sequence of elementary row operations reducing A to the identity matrix. So in other words, any product of elementary elementary matrices times A will give us I, and in reverse, we can transform I into A inverse. Well, let's see that happen. Okay, because this is going to give us the algorithm for calculating A inverse for any n by n matrix. So first, let's prove the first direction of the theorem, or at least look at the intuition for it. We assume that A is invertible, and we need to imply or get the result that A is row equivalent to the identity matrix. So if A is invertible, then for every B, vector B in Rn, AX equals B has a solution. Okay, we've seen that from a previous theorem. So by the equivalence theorem in section 1.4, A has a pivot position in every row. So this statement that AX equals B has a solution for every B takes us back to section 1.4's equivalence theorem, and we're able to conclude that A has a pivot position in every row of its echelon form. Well, A is n by n. If it has a pivot position in every row of its echelon form, then it has a pivot position all the way down its diagonal, its main diagonal. Well, if that's the case, its reduced echelon form will put ones in all of those positions down its main diagonal and zeros everywhere else. So we see that A is actually row equivalent to I sub n. It's that straightforward. What I might recommend is take a matrix like maybe a nearly reduced echelon form, something like this: 1, 3, 0, and then maybe 0, -2, 2. And there's an echelon form of a matrix A, right? We can further reduce this to reduced echelon form, right? Converting this to a 1 and this to a 1 with multiples or elementary matrix products, right? And then we can zero out above each of these terms in those columns, and we'll have a single main diagonal of 1s, and we'll have zeros everywhere else. And of course, this will be row equivalent to the identity matrix in 3 by 3. Again, that's just the 3 by 3 case, but that'll help develop a little further intuition if you're interested in that. So we've proved the first direction. If A is invertible, then it's row equivalent to the identity matrix. That's a useful piece of information. Let's show the other direction, the converse of that. So now if A is row equivalent to I, the identity matrix, then we have to show that A is invertible. So if A is row equivalent to I, assuming that there exists a series of row operations that reduce A to I. That's exactly what A being row equivalent to I means. So if we let these operations have elementary matrices E1 through EK, so say we do a number K of row operations to reduce A to the identity matrix, well then for each of those row operations, we have an elementary matrix E sub I, or E1 through EK. Okay, so if we multiply A by those elementary matrices, well, those are the row operations on A that we get to reduce it to I. Well, we have this string of products. We have E1 first applied to A, then E2 times that result, then E3 times that result, all the way up to our last one, EK times that result, to give us the identity matrix. Okay, well, each of these matrices, all the elementary matrices are invertible, and I don't go through all the details of what that statement looks like, but if we notice that if we apply, if we look at this matrix EK times EK minus 1 all the way down to E1, this is actually, its product altogether is the inverse matrix of A, because it times A is equal to I in this equation. So that's our inverse matrix that we're looking for in terms of elementary matrices. And we're stating that here, that A inverse is equal to this product of elementary matrices. Well, if we just go one step further in this statement I just highlighted and multiply that by the identity matrix, well, the identity matrix doesn't change anything, right? Because it is the identity. Well, we see that A inverse is actually equal to this same series of multiples of elementary matrices times I sub n. Now there's some more information about this where we can go the other direction. Each of these EK matrices or EJ matrices are invertible. So E1 has E1 inverse, EK has EK inverse, and everything in between. And we could multiply all of those times the side of this on the left, EK inverse, a series of reversed orders. So we put this in parentheses, make it in, take its inverse, and we can see we can multiply that by either side and get a similar result for these things. So the most important aspect of this is as follows. We see that in order to reduce A to the matrix I, the identity matrix, we can multiply by these elementary matrices, starting with E1 and ending with EK. Now, if we also apply that same series of products, EK down to E1, against the matrix I, then we'll get A inverse. So here's our algorithm, and this is moving down into the result below, for finding A inverse. We take the augmented matrix A and the identity matrix. So if A was 3 by 3 and I would necessarily be 3 by 3 then we'd have a 3 by 6 augmented matrix. All the columns of I would be added to the end of our matrix A. If we apply all of these row operations, E1 through EK against A, then we'll have I in our leading position. And if we apply all of these elementary row operations against I, then we'll have A inverse in the second position. So as the second 3 by 3 matrix in this augmented matrix. So the most fundamental way to find the inverse of a matrix A is to write the augmented matrix A sub I, or AI, and then reduce it to I, or to its reduced echelon form, and we'll have I A inverse. And if we don't have such a matrix, then A does not have an inverse. In other words, if we don't get the identity matrix right here as our first 3 columns in a 3 by 3 scenario, or our first n columns in an n by n scenario, then we know that there's no inverse to A. So not only do we get a check, but we have an algorithm in order to come up with it. So let's do that. Let's implement this algorithm. It'll be our last example in this section. So we're given a matrix A. It's 3 by 3. It could be a 4 by 4, 5 by 5, right? Any size will work. We're just using 3 by 3s because it's a little bit more, it's just faster and more efficient to calculate, but it's all the same process. So I've written my A, or my augmented matrix AI, and I need to convert it to IB. Of course, B will be A inverse, just chosen a different letter to be a little bit more general about it. But I need to put this into reduced echelon form. Remember, if something that looks like I, at least these leading ones here, are in this position, then we're in reduced echelon form. So that's what we want to do. The technique is always to, or the algorithm is always to write AI as the augmented matrix and then reduce it to reduced echelon form. So let's get to work. We have a leading one in position, top left, first row, first column already, so I'll leave that in place. I'll zero out both the 2 and the 4 below it, and I'll do that for the entire row, right? And then as we convert this matrix on this side to the identity matrix, the theorem of the previous page tells us that over here we'll be building A inverse by performing all the row operations that build the identity matrix here. We build the matrix A inverse, which is the inverse of A on the right. So what does this look like? We've got first row is still the same. We don't really need that separating bar in the middle. Just do it for emphasis. We have a 0, and then 2 and 1 is 3. 4 and 11 is 15. And then this is -2, 1, 0. And then for the third row, we've got 0. And then 4 and -3 is 1. And then -8 and 10 is 2. And this is -4. So let's swap rows 2 and 3 because I already have a 1 here. That should simplify some of this work. Remember, reduced echelon form is unique. So whatever way you choose to do this, we would both arrive at the same result. Row echelon forms are not unique. So maybe we would have something different, but we're not looking for row echelon. We want reduced echelon. So we have 0, 1, 2, -4. And maybe in this step, we swap them both. Let's zero out this 3, the same move. It's a little bit complicated, but you can take an extra step if you need to as the viewer. So we have 0, 0. So -3 plus this is +3 is 0. -6 and 15 is 9. 12 and -2 is 10. 0 and 1 is 1. And then -3 and 0 is -3. And so I swapped rows 2 and 3, or maybe before I did that, I zeroed this row, but all in one step, I swapped and zeroed a row. I need this, or would like this to be a 1. So I'll divide that whole row by 9 of 1. -1, 2, 1, 0, 0. And 10/9, 1/9, -1/3. So I'm pretty close. I need to zero out this and these two values. So in that case, we'll have 1, 0, 2 and 2 is 4. I'm adding row 2 to row 1. -4 and 1 is -3. This is 0. Have 1 here, and row 2 is unchanged. And I don't want to change 2 rows. I want to change them too quickly, so take my time. Got to zero out above this leading one. I'm almost there. I almost have reduced echelon form. It looks like this matrix is invertible, right? And in fact, it is invertible. We have a leading one, or we have a pivot position in every row. We already know that that's the qualification for this matrix to be invertible. We just need to find the inverse by making this the identity matrix fully, right? Or writing it so that it is equal to that, and extracting this information as our A inverse. So let's see, row 1 is going to change by -4 added times row 3 added to row 1. Nothing changes here. So we have a 0 here. -40/9 minus, this will be 27/9. So -40/9 minus 27/9 is -67/9. Then we have, let's see, -4/9. And we have 4/3 and 1 is 7/3. Then we'll have 0, 1. I want to zero out this 2 as well. So -2 times row 3 added to row 2. So this is a 0. And then -20/9 minus 36/9 is -56/9. Then I have -2/9. And then 2/3 and 1 is 5/3. And lastly, I just write the third row. And this really kind of turned out to be a pretty ugly looking inverse. Hopefully I didn't have an arithmetic mistake in the beginning. It's possible, but we could always check that later. I'll leave that to the reader to do so. But otherwise, the technique has been demonstrated reasonably well. -67/9, -4/9, 7/3. And we're just writing down our inverse matrix from what we found here. -2/9, 5/3, 10/9, 1/9, -1/3. So there we are. That should be our inverse, barring any arithmetic mistakes, but we see that the algorithm is pretty straightforward. We write this augmented matrix in this form, and then we need to convert that to reduced echelon form here, and then we'll extract our inverse matrix from the right hand, from the augmented matrix on the right. The other half is the way to think about it, right? For 3x3 matrices, we'll have two 3x3 matrices together forming this single 3x6. For any n by n matrix we're looking for the inverse of, we'd have an n by n here, and then another n by n here. So we'd have an n by 2n, 3x6, or 4x8, or 5x10 augmented matrix. And we just extract our other n by n matrix once we have an echelon form here. Now remember, if we don't get the identity matrix here, right? In other words, we have a row of zeros, and we have a pivot position over here at this 10/9 position or further right. And we don't have an exact copy of the identity matrix once we're in reduced echelon form, or if we have all zeros or whatever. If we don't see the identity matrix here for whatever n by n matrix we're dealing with, we don't have an inverse. So we just stop and say the matrix is not invertible. So that's it for inverses. We've started from the idea of what they are. And we're ending this section with the ability to calculate the inverse of any n by n matrix. In section 2.3, we'll take that a little bit further and learn how to find inverses for matrices with other techniques that are possibly more efficient than this one.